Thanks very much, Ben, for the invitation. I'll talk about machine learning from a mathematical perspective. So it's a little bit mathematical. I hope that's okay. Okay, so let me start with the basic formulation of the simplest problem in machine learning, namely regressions, which is a special case of supervised learning. So here we're given a data set where the data set is the function value of an unknown target function f star at some data points xj. And our task is to learn f star, namely try to approximate f star as accurately as we can. So this is the problem we want to solve. So this is the problem about functional approximation. This is very familiar, classical problem. Now, because it's going to be mathematical, so we'll specialize ourselves to the situation when the data comes from the unit cube, and mu is going to be the distribution of the sample points xj. So the standard procedure in machine learning to solve this problem is as follows. It's got 3 steps. The first step is to choose a hypothesis space, which is just a set of trial functions. So it's very much like a finite element trial function space. And we're going to denote that by hm. And m is roughly going to be the number of free parameters in this hypothesis space. For example, you can choose piecewise polynomials if you want to find elements. In machine learning, particularly in deep learning, people typically choose neural network models. That's another way to parameterize functions. The second step is to choose a loss function, namely to formulate an optimization problem in order to find the best approximation to f star. Remember, we want to approximate f star. Since we are given finite a number of function values, the simplest idea is just to fit the data, fit the so-called training data. And that means, we can formulate an optimization problem like this. We can define an objective function like this. We can also add regularization terms, and sometimes we do. So that's the second step. The third step is to solve this optimization problem with some algorithm like gradient descent or stochastic gradient descent. So that's a standard typical procedure. Now remember, and that's very important, what we really want to do is to minimize what is called the population risk. The difference between this so-called population risk and the empirical risk is that the empirical risk is defined with training data. And so it's also called training error. The population risk is defined with the testing data. So it's also called testing error. So that's defined in respect to all the sample points, averaged over mu. So this is the problem we want to solve. Now, some typical examples what machine learning can do. The first example is image recognition. Given a set of images, and you want to tell what the content of the image is. So this is a very familiar CIFAR-10 data set. All the images contain one of the contents of the images are divided into 10 categories. And you're supposed to tell the category of each image. So that's an image recognition problem. That's a classification problem because the f star takes a discrete set of values, so actually 10 values. As an example of regression, so here is to try to find the interatomic potential in the material or in the molecule. So the atomic potential describes the interaction between atoms and is a function of the positions of all the atoms in the system. So either a material or a molecule. And we want to fit this function. We want to fit the function to quantum mechanics models. We want this function to be as accurately as quantum mechanics. So the data is computed using a quantum mechanics model, for example, density functional theory model. That's the most popular quantum mechanics model used in practice. And here are the results of a particular deep learning model called deep potential model. And you can see across the very wide range of molecules and materials, starting from small molecules, this is aspirin, this is ethanol, and this is big molecule like pyridine. And these are simple metals or alloys. And this is a very complicated system, so-called high entropy alloy. It's called 5 components, oxidides, and etc. So across the whole wide range of systems, the accuracy is pretty much as good as the accuracy of the quantum mechanics model. And third example, what you're looking at are images of a human face. And all these images are fake. You can see they look really, really real, but they're all fake. So what is done here is as follows. We view pictures of a human face as being a random variable in the space of images. That's a random variable. But we don't know the probability distribution of that random variable. What we do know is a finite set of sample points, namely pictures of real human faces. So from that finite sample points, a set of finite sample set, we can actually construct a very accurate approximation to the underlying probability distribution. And we can actually use that approximate probability distribution to sample new points. And these new points are what you see. And these are pictures of fake human images, human faces. So that's a third example. Fourth example is, the AlphaGo. So everybody probably knows that. But what I want to emphasize is that given the strategy of the opponent, the Go game can be formulated as a Markov decision process. So there are some details associated with that I'm going to skip. But let me just want to say that the Go game can be formulated as a Markov decision process. Then the optimal strategy solves a corresponding Bellman equation. So what AlphaGo does is just try to solve a Bellman equation in a huge space. So if we look at these examples, approximating functions, approximating probability distributions, and solve equations, these are all classical problems in mathematics, particularly computational mathematics. The difference here is the huge dimensionality. If we go back to the first example here, each image, if you look at how many, the dimensionality of the problem, to count the number of degrees of freedom, each pixel is a degree of freedom. And the number of pixels is 32 by 32. And then the space of color is 3-dimensional. So really, this is a 32 by 32 by 3-dimensional problem, 3072-dimensional problem. So we're approximating a function in the 3072-dimensional space. So all these examples, either they're very high dimension or they're in a huge space. And these are the kinds of problems we never imagined being able to do before. Now, these are made possible now because of our ability to accurately approximate high-dimensional functions using a finite piece of data. And we're able to do this basically because of deep learning. So this also opens up, so this is the first important point to realize. The second important point to realize is that this also opens up new possibilities for attacking problems, traditional problems, more traditional problems, not in the area of AI, but traditional problems in science or scientific computing that suffer from the curse of dimensionality. So curse of dimensionality refers to the problem that as dimensionality grows, computational cost grows exponentially fast. Because of COD, we were not able to solve high-dimensional problems before. So now let's take a look at the second possibility, namely solving very high-dimensional problems with the help of deep learning. My first example is stochastic control. And I use this example for two reasons. First is that I think is the very first example where deep learning is used for solving problems in scientific computing. That's the first example. The second example is that stochastic control has a very close similarity with deep learning. And that's actually the motivation to look at this problem several years ago. So this is a stochastic control problem. Z is the state, A is the control, and C is the noise. We have a discrete dynamical system, and we want to choose the control to minimize this the objective function, which has running cost and terminal cost. And we're going to look for feedback control, namely control as a function of the state. Now, if the state has high dimension, then this is a high dimensional control problem. And we're going to approximate this control function, policy function, by a neural network. Never mind the details of that neural network. Well, just think about this as the abstract neural network. Then the objective function becomes this. We want to minimize this over the space of the parameters for the neural network. We have total T neural networks. T is the sort of the horizon for this control problem. So we have T neural networks. It's got T set of parameters. We want to minimize this objective function over that set of parameters, subject to the discrete dynamical system that defines the control problem to begin with. Now, I want to claim that this is a very close, there's a close analog with deep learning, particularly ResNet-based deep learning. Now, in analogy with deep learning, this guy, this discrete dynamical system, plays the role of ResNet. And this guy here, which is the stochastic control problem, it's a objective function is an optimization. But this E here is the important part. So that's the analog of the empirical. We can use SGD. So the framework of SGD and ResNet applies pretty much directly to this stochastic control problem, and that's how that's why we decided to use this as the first example to illustrate the power of deep learning when applied to high dimensional problems in classical scientific computing. Here is an application, and it's a made up example, energy storage with multiple devices. N is the number of devices. This is 30, 40, 50. And as you see, this is the convergence history as we optimize using SGD. You can see that it converges nicely and the error bar is pretty small. The second example I want to just touch upon, not discuss in any sort of detail, is to solve high dimensional PDEs. This is a nonlinear parabolic PDE. Well, initial value problem. Now, this problem, with the help of so-called backward stochastic differential equation, BSD. If you don't know BSD, it's okay. Now we're just using BSD to formulate this PDE problem, very much like a stochastic control problem. So I claim that this PDE is equivalent to this control problem, where the objective function is this guy, and subject to the constraint, which is a dynamical system, which is a BSD. Now, okay, the details don't matter, but what's important is that we can formulate the PDE problem as a stochastic control problem, and then we can use similar ideas to what I just described and develop deep learning-based algorithms, and these algorithms can be used to solve very high dimensional PDEs. This is a very simple linear quadratic Gaussian control problem. Again, it's a control problem, but it's a continuous time where M is the control, W is the Weinan process, and lambda is just fixed parameter. People try to solve this problem in 2 and 3 dimensions. Here we try to solve it in 100 dimension. Sorry, I forgot to mention that the cost function is just the simple cost function. And then for this stochastic control problem, one can write down the Hamilton-Jacobi-Bellman equation. And this is the classical celebrated Hamilton-Jacobi-Bellman equation. If you know PDEs, you know that there's a Hopf-Koh transformation that sort of linearizes this particular nonlinear PDE. Using that, we can write down this formula for the solution. And this is the formula. So we can use this formula to calibrate the deep learning based algorithm. By the way, we call that deep learning based algorithm deep BSDE method. So we're going to use this formula to calibrate that. And you can see that, as this is the parameter. The horizontal axis is the value of lambda, and the vertical axis is the solution at a particular point. You can see the agreement is pretty good. And my collaborator Jichen Han has maintained a open source platform where people can play with these games. Now, I should also mention that I think this is the very first deep learning based algorithm for solving PDEs. People have been using neural networks to solve PDEs in the in the 90s, basically using neural network as the trial function for in the setting of nonlinear Galerkin method. But using PDEs, using deep learning based algorithm to solve high dimensional PDEs, I think this is pretty much the first work. Since then, there's been a lot of work. Perhaps the close related is what is called deep Galerkin method, DGM, and then there is PIN, physics informed neural network. So those are different set of ideas in the sense that they use least squares. I mean, the formula PDE problem has a least square problem, and in the case of PIN, it's pretty much used to solve low dimensional PDEs. So in that setting, it's not absolutely clear at the moment what the advantage is. Use that as a direct solver for low dimensional PDEs. But it has got other potential. For example, you can try to use neural networks to parameterize the whole solution operator and stuff like that. So there's a lot of room for research in that direction. But very clearly, as a way of solving high dimensional PDEs, deep learning has is particularly powerful. And the deep BSDE method, in developing the deep BSDE method, we try to make the point that the underlying structure is also important. We thought about doing Galerkin, but we sort of thought that exploring the underlying structure is also important. And here, by the underlying structure, I mean the stochastic control formulation of this particular PDE. Anyway, I think this is something to be considered, still to be considered. The third example, I think I should run quickly, is the molecular dynamics. So molecular dynamics I already mentioned actually in the interatomic potential example. It's just to solve Newton's equation for the position of the atoms. And then you need this potential, V. So I illustrate before how to use deep learning to get this potential V. And this has been quite successful, as I showed earlier. And combined with high performance computing, we've been able to extend ab initio molecular dynamics. So molecular dynamics with ab initio accuracy, quantum mechanics accuracy, from being able to handle like 1,000 systems to being able to handle 100 million and now billion systems with a billion atoms. And this is a huge advance in terms of the size of the system. Again, we've also developed an open source platform. Actually, my collaborators have developed this open source platform. And it seems like deep learning is really the missing tool for the multi-scale modeling program that we've been pursuing. The scientific community has been pursuing over 20 years ago. It was very popular and exciting, 20 years ago, the multi-scale modeling program. And something was missing. I always felt something was missing. It seems what was missing is really the tools like deep learning. And now there's, of course, the whole spectrum of different hierarchy of physical models. There's, exciting work done on using deep learning based algorithms to solve these problems, from solving Schrödinger equation to developing better DFT models, classical molecular dynamics. I just mentioned coarse-grained molecular dynamics, solving Boltzmann equation, all these different hierarchy of physical models. There's very exciting deep learning based algorithms. Okay, let me now turn to the main theme of this talk, namely try to understand the mathematics or principles behind deep learning. So there are two kinds of questions. One is to understand the mysteries about deep learning. Now, two particular important questions. One is, why does it work in such a high dimension? And second is, why is it so fragile? We all know that training deep learning models is a rather difficult task. You know, the performance depends sensitively on the parameters. So why is it so fragile? And the second question is to try to formulate better machine learning models, like, you know, for example, ODE-based models, or, you know, other. So these are the things that we need to. These are the motivations behind looking into machine learning from a mathematical viewpoint. Now, let me first make a remark about high dimension. So if we think about high dimension, there's one particular problem that we've been solving in high dimension pretty much routinely, and that's the problem of computing integrals. If you want to compute this integral, okay, if you use classical like quadrature rule, Simpson's rule, trapezoidal rule, it's going to have cursive dimensionality. The error grows like goes like 1 over m to the alpha over d. M is, remember, m is the number of parameters, and this 1 over d is the source of cursive dimensionality. For example, if you want to make this to be 0.1, if you want to make this factor to be 0.1, then m, the number of parameters, needs to be 10 to the d if alpha is equal to 1. Alpha is a, you know, fixed number. So if d is 3,000, this is huge. So this quadrature wouldn't work. And what does work is Monte Carlo. So we do Monte Carlo, namely choose these xj's to be ID random variables uniformly distributed in the cube. Then we know this is exact. This is exact, and the error squared goes like 1 over m. There's no 1 over d in exponent. So the convergence rate does not depend on the dimension. Of course, this coefficient could be huge in high dimension. So that's why variance reduction is important. But in any case, Monte Carlo's integration is a very successful area, and we can compute integrals of millions of dimensions quite routinely. So this is pretty much the benchmark that we have to keep in mind. So coming to our problem, so let's remember f star is a target function, and let's denote by f hat the output of the machine learning model. We want to decompose this error into 3 parts. In order to do that, let fm be the best approximation in some sense in the hypothesis space. F hat is the best approximation that uses data. Now, if we only allow to use the finite sample points, what are the best we can do? Hello? Okay, so we can decompose this error into 3 parts. The first part is the approximation error. So this is the best you can do given the hypothesis space. The last part, the second part, is the estimation error. This is the additional error due to the reason that we only know a finite sample points. We don't only know finite training. We only have finite training data. And the third component, the third part, is the optimization error. This is the error caused by the training algorithm. Now, the training algorithm may not be able to give you the best result. So that, okay, so let's look at the 3 pieces separately. What about the approximation error? Well, the approximation error in the classical approximation theory, when you approximate by piecewise polynomials, you get this, and this has got the cursive dimensionality. For the estimation error, there's also a classical example. So this is the polynomial interpolation on a finite number of grid points, equally spaced. And you can see that we're interpolating a very nice function. But you know, on the interpolation points, there's no error, but away from the interpolation points, away from the training data, you can see there's huge error. So this is the classical wrong phenomena. And we don't want that to happen. So how do we guarantee that that doesn't happen? How do we, well, we want this so-called generalizing gap, namely the test error and the training error, the gap between the two to be small. If you look at these guys, the definition of these guys, this is the training error. Sorry, this is the testing error. This is the training error. You get the, you might get the impression that the one is just the Monte Carlo discretization of the other. So therefore, the error should be 1 over square root of n. That's not the case, because this guy f hat is very much correlated with the data. As a matter of fact, this correlation is really the complication. For example, if you choose the hypothesis space, so in the end, this really depends on the hypothesis space. If you choose the hypothesis space to be the space of all Lipschitz continuous functions with Lipschitz constant 1, take that to be the hypothesis space. Then the generalizing gap goes like 1 over n to the 1 over d. Remember, n is the size of the training data set. So this is another source of COD. This is the COD for the size of the data set. As dimensionality grows, the data you need grows up exponentially. We don't want that to happen either. So how do we control this gap? Well, this is done. One of the ways to do this is through the notion of Rademacher complexity. So Rademacher complexity is defined with respect to a set of functions. Let H be a set of functions, and S is just our data set, training data set. The Rademacher complexity of H is defined to be the ability to approximate noise using the functions in that set of functions. So Xi are just random variables taking the values plus minus 1 with equal probability. So that the supremum means that you want to approximate Xi as best as you can. So that defines the Rademacher complexity. And the reason that Rademacher complexity is helpful is because that controls the quantity we're interested. This was the quantity we're interested. Since we don't know how to, since there's a lot of correlation, we control this by the upper bound, by the supremum over the whole set of trial functions. So this quantity is controlled above and below by Rademacher complexity. So, in other words, the Rademacher complexity for Lipschitz functions is given by this 1 over n to the 1 over d. That's so we want this Rademacher complexity to be small. So, given the consideration that we had before, we can summarize machine learning models into 2 categories, 2 kinds. The first is the kinds of models for which the generalization error, so either approximation error or the estimation error suffers from COD, namely there is 1 over d in an exponent. So the classical piecewise polynomials, wavelets, they belong to this class. And the second are models for which don't suffer from COD. So we expect the error to be like 1 over m, 1 over square root of n. This would be the Monte Carlo. This would match the Monte Carlo rate. And we expect the modern machine learning models to fall into this category. So particularly deep learning models to fall into this category. The question is that true? Of course, we didn't consider optimization error. So we're going to briefly mention that at the end. So the general procedure would be to control the optimization error, the estimation error, and to see whether these kinds of error control is possible. Okay, so let me give you some simple example for which this is true. Well, and we need to ask, in what sense is this true, of course? So consider the so-called random feature model. So random feature model is the following model. So let phi be a function parameterized by a random variable w. So w here is a random variable. It's called the feature vector. So this is just a function parameterized by w. And pi is the probability distribution of that parameter w. For example, we can take phi to be this guy, where sigma is some nonlinear function, like the activation function in neural network models. Okay, so let's take a IID sample of pi, call that omega j. So this is a realization IID sample of pi, and fix them. And then consider this model where, so linear combinations of phi with wj. So this is a linear model. It's called this is called a random feature model. And for this random feature model, let's define the particular set of functions. So consider functions of this form, where can be f can be expressed in an integral form like this. So there exists a function a such that f is given by this integration. And let's define an fp norm to be the piece moment of the coefficient a. Okay. Now, if a is not unique, we also need to take an infimum over a. Now, if p is equal to 2, then this space is nothing but the so-called reproducing kernel Hilbert space associated with this particular kernel. So from this feature function, we can define this kernel. So random feature models is closely related to kernel methods in machine learning. And F2 is just the classical reproducing kernel Hilbert space. Now, one can prove the following direct and inverse approximation theorem. If a function belongs to the space of f infinity, so namely the coefficient a is essentially bounded, then for any small parameter, small value of delta, with the probability of 1 minus delta over the random samples of wj, there exists an coefficient function a such that this error, this test accuracy, this coefficient set of coefficient aj, such that the test error is bounded by 1 over m, and with coefficient this f infinity norm squared. So this is the direct approximation theorem saying that the approximation error goes pretty much like a Monte Carlo rate, except for these logarithmic factors. The inverse approximation theorem states as follows: if for the function f star, if the function f star can be approximated by the random feature model, and the coefficients aj are uniformly bounded, suppose f star has that property, then the f infinity norm has to be finite, namely f star has to belong to the space f infinity, and it's got this representation. So this is the direct and inverse approximation theorem, which says pretty much that for the random feature model, there's an associate function space, namely f infinity, and for that for which the direct and inverse approximation theorem holds, and the error, the convergence rate, does not depend on the dimension. Now, so that's the approximation error. In order to look at the estimation error, we need to look at the Radamar complexity. So this theorem states that if you consider unit ball in F2, so this is not infinity, we can prove the similar theorem, then the Radamar complexity goes like 1 over square root of n. Remember, this is pretty much the best you can, best that we can get, except with this logarithmic factors depending on the dimension. So that's the Radamar complexity control. Then given these two results, approximation error, approximation theory, and Radamar complexity estimates, then one can show the following. If we consider a regularized model, so with this regularization, and this is actually the typical regularization one should consider. The scaling here is a typical scaling that one should consider. If you look at compressed sensing or a lasso, you will see these similar kind of scaling. And then one can show that global minimizers for this regularized model satisfies the following, namely for any delta with the property 1 minus delta over this choice of the training data set, the test error, so this is now the result of solving a real machine learning model. So here, this is the optimal approximation. This is not solving the real machine learning model. So here this A is the solution of the real machine learning model. So the test error for that machine learning model is bounded by 1 over m, 1 over square root of n, up to some not very important terms. So these are the kinds of results we hope to see. And you can see for the case of random feature model, indeed they're true, they hold, but with the caveat that we need to regularize. And then you need to ask, what happens when we don't regularize and we solve with some particular optimization algorithm. So that we'll briefly discuss later. The second example is the 2-layer neural network model. So this is a 2-layer neural network model where now sigma is the activation function. So this ReLU activation function, for example. And you see that this looks very much like the random feature model, except that Wj is not fixed anymore. Wj is also allowed to change. It's also the parameter that we want to optimize. Now, for this particular 2-layer neural network model, it's called 2-layer because we've got 2 sets of parameters, Aj and Wj. And if you draw this diagram with the neurons, you'll see that there's an input layer and there's a hidden layer. And this is what I call 2-layer. And then, so for this 2-layer neural network model, we want to define the associated function space for which the directly inverse approximation theorem holds. In order to do that, let's consider functions of this type, namely functions that emit this kinds of integral representation. See that this is the analog of this. No. Okay, we need to look at functions of this kind of integral representation and similarly define these new strange looking norms, which are defined through the mixed expectations. And these functions for which, continuous functions for which this norm is finite, we call them Barren functions. Now, let's make a comparison between, and this space is called a Barren space. So how is this space related to the reproducing kernel Hilbert space? Now, this was what we had before, and there pi was fixed, a fixed probability distribution. And this guy is very much like this, except now rho also changes. It's not fixed. So symbolically, one can write Barren space as the union of all reproducing kernel Hilbert space. The unions over all probability distributions pi. So you can see that, well, first of all, this space is bigger than this. And you see that, 2-layer neural network is pretty much like a random feature model, except that the feature function itself is learned. So it's sort of an adaptive random feature model with adaptive kernel. And that ability to choose the right kernel is very important. And that's the difference between neural network models and random feature models. For example, if you know about SVM would be perfect if the right kernel is known. And the real difficulty in practice is that we don't know the right kernel. Okay, anyway, that's a side remark. Okay, so for that, with that definition of Barren space, one can also show direct and inverse approximation theorems, and they're pretty much similar. You can see I sort of so direct approximation theorem says that any function Barren space can be approximated by 2-layer neural networks with a convergence rate, which is like 1 over square root of m. And the inverse theorem says that if a function can be approximated by 2-layer neural networks, and these neural networks have some uniform bounds, then that target function has to be a Barren function. And again, we can show that Rademacher complexity is like 1 over square root of n with some logarithmic dimension dependence on dimensionality. This theorem was proved by Bach. And together, we can consider, regularized models, similar kind of regularization. And then you can show that minimizers, global minimizers of the regularized model satisfies the following estimates, namely the test error is bounded by 1/m and 1/√n, and then the coefficients are Barren norms, and these are unimportant logarithmic factors. Okay, so this is for two-layer neural network models. Now, let me just say that similar kind of results have been proved for ResNets, in which we define something called flow-induced space, in the analog of Barren space or reproducing kernel Hilbert space. It's also proved for multi-layer neural networks, like 3 layers, 4 layers, 5 layers, and in which we define something called multi-layer spaces. Except that in this case, for multi-layer neural networks, we were not able to prove results of this type. This is the kinds of results we wanted to prove. Indeed, for ResNets, we do have results of this type. But for multi-layer neural networks, we were not able to prove results of this type. There were some stuff in here that didn't depend on dimension, so there was no curse of dimension, but they're dependent on the number of layers. So there's a curse of depth of the neural network. So that's quite unsatisfactory, and I hope people, and that discrepancy, I think, is not just technical. I think it's conceptual. If you note, I don't know whether you've noticed that all these, these line of thoughts are based on the idea that the particular values of the parameters don't matter. It's the probability distribution of these guys that really matters. So, the theory is built upon this basic starting point, and how we can do that for ResNets, for two-layer neural networks, for random feature models, etc. But for multi-layer neural networks, and there is still an important gap in terms of thinking about as in the space of probability distributions. Okay, let me say something about a training error. I think I should. Okay, so there are two questions. One is optimization. Does the training process converge to a good solution? And how fast does it converge? Here, a good solution means that training error is small. That doesn't mean that the testing error is small. They could be different. The second question is that for the solution, how about the testing error? Is the testing error also small? And remember, testing error is really what we like. Okay, that's the question we want to have to address. So in this connection, let me mention one result, and that's associated with what is called mean field formulation, and it's developed independently by a number of different groups. And again, we're considering two-layer neural networks. We're thinking about the probability distribution of these parameters. Now, okay, let's denote these set of parameters in a shorthand by uj. Now, the training error is a function of the parameters u, and the GD dynamics would be the gradient descent of this objective function. So this is the GD training dynamics. Now, what's interesting is that I think actually I made this observation. These guys proved convergence, but actually I made the observation that that you don't need to think about convergence. You actually this GD dynamics is an equivalent formulation of this mean field PDE, or integral differential equation. So the claim is as follows: if we define a probability distribution like as follows, given a set of parameters at time t, define this probability distribution, and claim that this probability distribution actually solves the following PDE, where V is this the potential associated with the model. Now, these guys actually proved as m goes to infinity, it converges to this. And the claim I'm making is that you don't need to take m going to infinity this, it's exact for even for finite number of neurons. Now, what's important is that this is nothing but the gradient flow of the training of the empirical risk under the Wasserstein metric. So this is a kind of problem people look at in optimal transport. So the expectation was that the tools from optimal transport would apply here and it would help us. And that so far has not been very successful. And basically because that these functionals, these objective functions are not displacement convex. So whatever that means, it's not important if you don't know what displacement convex means. But because of that, we cannot use directly the results from optimal transport. But there's one interesting result that I want to mention, and it was proved by Jasenbach and my former postdoc Wojtowski made an improvement, which basically says the following. This is really a messy theorem in terms of the conditions. It basically says that if the initial condition is such that, if the initial rho 0 is such that it has full support and it covers everywhere, the support covers everywhere. And if there's convergence, so rho converges to some limit, then that limit must be a global minimizer. So it cannot converge to some local minimizer or saddle point. That's not possible. If there's convergence, then it must converge to a global minimizer. Of course, there may not be convergence, it might oscillate, and that's the bad. That would be bad, and no one has been able to show that that doesn't happen. And of course, if proving convergence is not enough, when you really need to understand the convergence rate. And there are counterexamples that showing that the convergence rate can suffer from the curse of dimensionality. So Stefan Wojtowski and I have a paper on that, if you're interested. So these are still very important questions that we don't know how to handle. And let me show you what happens in practice. So what happens in practice that we take these kinds of formulation, the difference between this two-layer neural network and this two-layer neural network is that there's a 1/m, and here there's no 1/m. That difference looks small, but actually causes a big difference in the training dynamics. Anyway, if we take usual initialization, namely choose these coefficients AJ to be normal, to be normal random variables, Gaussian random variables, and then just run, and let's ask what happens. Well, in order to answer that question, let's define an associated random feature model. And that associated random feature model is the following, that we take BJ and just fix the BJ at the initial condition. And don't let it move. And then only train AJ. And that is a random feature model because the BJ, these guys are fixed. I used to call them W, by the way, I'm sorry. And so that would be a random feature model. With that random feature model, one can define a Gram matrix as follows. So here's an important theorem that has two parts. Okay, so consider the situation for which M is much bigger than N. M is the size of the neural network, the number of neurons. N is the size of the training data. So this is called highly over-parameterized regime. Namely, the number of parameters is much more than the number of training, the training data size. So in this fashion, lambda n is the smallest eigenvalue of this matrix K. Okay, and that the size of which can be estimated. Then the following is true. The following two are true. First of all, there is exponential convergence of the training error. Okay, that's true. Secondly, the function we get from this training process is uniformly close to what we would have got if we use the random feature model. Namely, don't train the inner parameter B. And so there's uniform closeness with this too. So that means, even though the training error converge exponentially fast. The model itself is no better than the random feature model. So I think this is really bad news, because this shows you that the neural network doesn't have much of an advantage over the random feature model in this regime. In the community, this regime is referred to as a neural tangent kernel regime, and it's got a lot of attention, lot of attention. Without, like, okay, I think it's pretty much, a lot of the there's a lot of huge waste of time associated with this, but it's important to know this is true. But it's also important to recognize that this is very much of a counterexample of what bad things could happen in over-parameterized regime. I think most people I've talked to have not realized this. But I mean, and let's just take a look in practice. Let's take the target function to be this target function, a single neuron. This is just sigma of x1, sigma of x1. And look at two situations. The first situation, look at the bottom. The first situation is m is much bigger than n. So m is 2000, n is 200. And you can see that the red curve is the random feature model, and blue curve is a neural network model. And you see there, both the training curve and the testing curve are very, very close. And the results are very close and very much random. If you look at the other regime, and here n is infinity, and for this particular case, we can actually calculate the whole thing so that we can use n to be infinity, the training data to be infinity. And m is 200. And then you can see that the two curves are very much different. This is the random feature curve, and this is the neural network curve. And you look at the solution, they're also different. The random feature is pretty much random, and for the neural network, almost all the coefficients are small except for 2 spikes. So in this regime, the behavior is very different. And this is a regime we're interested in. So understanding what happens in this regime still requires some effort. And if you look at how the test error behaves in the space of hyperparameters, m and n, and log m and log n, you see there's a phase transition almost. The phase transition, there are two phases: a bad phase for which the error is big, and a small phase for which the error is small. So that shows that the error depends sensitively on the choice of the hyperparameters. If you're not lucky and chose your hyperparameter, the hyperparameters to be in this regime, then it'd be bad. The behavior would be bad. And this is just for 2-layer neural networks. Imagine what happens in multiple layer neural networks. Then this phase diagram would be more complicated, and training the tuning parameters would be harder. In contrast, if you look at the mean field scaling, the difference is only whether you have one of m or not. And you can see that it's pretty smooth. However, as I noted earlier, this is only for 2-layer neural networks. For multi-layer neural networks, we still don't know the formulation. Let me finish. I don't know whether I should just skip or, let me just go through this quickly. So the last point I want to make is to use optimal control kind of ideas to develop new training algorithms. You can see that if we, so as Ben mentioned earlier, I started doing using ODEs to formulate ODE-based machine learning models in which we just use test function to be the result of some ODE where phi is some particular feature function and tau is the parameter time tau. And then from the flow map, you can form a function and use that kind of functions as test functions for the machine learning model. In that case, this becomes very much of a control problem. This would be our objective function. And then we can, control theory, we have maximum principle. So this is convergence maximum principle, where we're Hamiltonian, and then maximum principle claims, that's the most important statement, that at each value of tau, the optimal control solves this particular optimization problem, and where the z's and p's are the states and co-states, and solve this forward and backward equation with some boundary condition. And based on that, one can formulate training algorithm. And training algorithm goes as follows. Since time is running out, let me skip. And then the training algorithm is very competitive. Compare with stochastic SGD kind of algorithms, converges much faster. These are SGD, particularly when you have a bad initial start. So these two sets of results are for initial conditions for which you have a small variance, big variance. Big variance is usually harder. You can see the harder, the better. So summarize. So if I think back, what we have really learned from machine learning, it's actually these kinds of things, representing functions as expectations. So I explained pretty much this particular situation. I didn't explain these following. These are the two. So this is associated with ResNets. ResNets actually, behind ResNets, we have this particular formulation, representation of functions. Behind multilayer neural networks, the kind of multilayer spaces we defined that I said was not satisfactory, there's this kinds of representation of functions as expectations. And I think this is essential, mostly essential component that we need to think more about. And then, to summarize, I think what I presented was very much a numerical analysis viewpoint of machine learning. Approximation theory, solving algorithms, discretization, etc., convergence of optimization algorithms. And I think this is an important avenue that we need to keep thinking about. Thank you very much. I think I'm running out of time.
Well,
Thanks.
Thank you very much for your talk. That was fantastic. So we have a few minutes left for questions.